So today we will go through some of the applications. Okay. Say we have known some applications like this. So there is one rocket. So basically what happens into the rocket is, say one fuel, say a fuel, say hydrogen, mixes with oxygen at a chamber downside here, and then their combustion reaction will produce heat. Because of the heat, the atoms or molecules of the products of combustion will get out. But in what way they get out, there is a particular logic for that. So that is, say, the rocket engine. Now in the rocket engine, so on the right hand side there are two pipelines and one mixing chamber. Say at one location hydrogen will come, at say just behind it there is another pipeline, there would be say oxygen, and then there is certain arrangement here why it goes downside, why the shape is like this, and then it again comes up, and here the combustion reaction would occur at this location. Now because of that, the gases will now pass because of the shape of this device. Look at the bell shaped curve. This particular shape, which increases velocity, which increases velocity, is called as nozzle. So ideally speaking, how you can draw a nozzle? So let us say this way. This is a horizontal nozzle, this is a vertical nozzle, so this is the axis of the nozzle. So the gases will move out of the nozzle at a higher velocity. So at the inlet the velocity would be low. So this particular shape increases the velocity. Now we have utilized another principle, that if this is the flow direction, then mass into velocity, so action to reaction principle, so the rocket will move upward. But let us focus only onto this nozzle. So hydrogen, oxygen combines into the combustion chamber. So hydrogen need to flow from the tank to the combustion chamber. So there would be a very low velocity, and when they will get out, there would be very high velocity. So for this, if we apply the steady flow energy equation, then what we can write down is, say Q is equal to W plus delta H plus delta KE plus delta PE. This is the steady flow energy equation. For the nozzle, look at the shape of this nozzle. We can assume that the heat transfer in and out is negligible. or it is 0. Similarly, the work transfer integration PdV is also 0. The potential energy change, this is the location 1, this is the location 2. Now there will be some potential energy change, but compared with the other energies, this potential energy change is also negligible. So final equation what you get is H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. Now continuity equation. Continuity equation, mass flow rate, area, cross sectional area, velocity upon specific volume. So at the location 2, the same quantities, area, velocity and specific volume at the 2. Now let us compare the V1 and V2. Now say V1 might be say 10 meter per second, and at the exit here it would be say 10,000 meter per second. So V square by 2, V2 square by 2. So square of this. So how much it is? Just 100 by 2. And how much is this? Say 1, 2, 3, 4. So 10 to the power 8 divided by 2. Now compare this figure with the outlet figure, outlet velocity. So I can assume that the velocity at the entry, I can neglect it. It is not 0 in real situation, but comparing with the other quantities, I can neglect it. So finally what I can get, velocity at the outlet will be equal to under root 2 h1 minus h2. Okay. So what you can get? So initial velocity v1 is say 0. So final velocity v2 will be equal to under root of 2 into enthalpy difference. Okay, so what is the basic function of nozzle? That it converts the enthalpy into kinetic energy. What is this conversion? It converts the enthalpy into kinetic energy. Means what? Temperature, pressure, specific volume, this sort of energy, or the energy which is there inside the flowing fluid, is converted into kinetic energy, and then we have utilized this kinetic energy for our purpose. So remember what is the formula for the change in kinetic energy? The enthalpy difference. The enthalpy difference goes into change in kinetic energy. So this is the way we increase the velocity. Say let it be a test rig at a location here inside. You can assume the velocity v0, and at the exit there would be a very high velocity. So these velocities will move at a supersonic speed. So what is the sonic speed? Sonic means say sound. So speed of sound at 1 atmosphere and 30 degrees Celsius is somewhere around this value. This is the speed of sound. Supersonic means what? The speed of the gases is more than the speed of sound at that particular pressure and temperature. So for a supersonic speed, the nozzle shape becomes like this. So initially it will gradually decrease, the cross sectional area decreases, later on it will increase. Later on it will increase. So this is the representation of a nozzle. The nozzle is represented like this. So maybe up to the sonic speed, the nozzle is converging. But after the sonic speed, as the molecules attain more than the velocity of the sound, the same nozzle is diverging. Diverging shape. So converging shape, diverging shape. Okay, so that is why for a very high velocity you can look at the shape of the nozzle like this. But when the velocity is not sonic, it is subsonic, that time look at the shape of the nozzle here. Look at the shape of the nozzle. So basically what is happening, apply the first steady flow energy equation. So through a pipeline, obviously here there is a pump, again it is a device, so there would be its own steady flow energy equation. Pressurized fluid, pressurized water is flowing from the back side of this person, and then simply it is getting diverted to the two sides. The velocity of the particles of the water are below sound velocity, so we have to use the nozzle design like this. The cross sectional area decreases, so the velocity increases. Here area A1 V1 upon density, specific volume is equal to area A2 velocity V2 upon density V2. Now for the water, density is almost remains same, so this will get cancelled. So area, higher area, lower velocity, the product is here. Lower area of cross section, higher velocity, the product is to be calculated here. Okay, so A1 V1 is equal to A2 V2. So for the fluids where the density do not change, that time the nozzle is of converging shape. What is the shape? Converging shape. And then there are other calculations. What is, if we calculate the velocity, then further we can calculate that how much force the thrust of this nozzle is producing. So this is a nozzle. Now let us look at one another application. This is a diagram of a aircraft. So aircraft is made up of some material, some metal. So what is happening? Let us say this is the center of gravity of the aircraft. So gravity will pull down. Now you want the aircraft to move from one place to another place. So as the aircraft moves ahead, the air will try to resist. So there is a resistive force on the right hand side direction. This resistive force is called as drag. Now for this gravitational pull downward, you need an uplift force. For that uplift and for this drag, we need to push the aircraft towards left hand side. So for that, in order to make the aircraft move towards left hand side, we incorporate one engine, say called as jet engine, whose function is to throw the air mass into the opposite direction as that of the movement of the aircraft. So that then there is another principle. So for every say aspect there is another physics involved. So for that there would be the action reaction principle, and hence the aircraft moves ahead. As the aircraft moves ahead, because of the wing profile, the uplift force gets generated, and that will cancel the gravitational force, and this drag force will be cancelled by the jet engine exhaust. So this is the exhaust. So again at the jet engine outlet here, just look at this place at the outlet. This is a nozzle which will throw the air mass at a very high velocity. So to increase the velocity, we have to decrease the enthalpy. Enthalpy decrease increases the velocity, and hence the aircraft moves forward. Let us see another application, say a turbine. So basically what is a turbine? So let us say there is a high pressure, high temperature steam. So pressure temperature high means the enthalpy will be high. So that steam will pass through an expanding portion. So look at this portion, this is an expanding portion. Now on the left hand side, the diagram represents almost all the details of how a turbine is made up of. So here at the entry, the cross-sectional area, the passage through which the steam passes is small, and here at the exit, the cross-sectional area or the passage through which the steam goes out is large. So basically you see a diverging nature. So I can draw a turbine like a diverging section. Now diverging section represents that at the entry, whatever is the specific volume will be less than whatever the specific volume at the exit. So this is the location 1, this is the location 2, or when the steam will come into this chamber, this is the location 2. This is the location 1, and here the location 2 is this. So steam flows through a passage. Inside that passage, what arrangement, what exactly shape of the devices, equipments, components of the machine are used. So don't think about what exactly the shape is. For that there are other subjects. But on an overall basis, just see that the steam at a higher pressure, higher temperature, means higher enthalpy, will pass through certain expanding chamber, thereby lower pressure, lower temperature. So this will imply lower enthalpy. And then there is another mechanism which will rotate the shaft, and that shaft is connected to the generator, etc. So forget that thing. So here, for the turbine, what will be the steady flow energy equation? So steady flow energy equation for the turbine, say I can write down in a elaborated form: h1 plus v1 square by 2 plus z1 gz1 plus q is equal to w plus h2 plus v square by 2 plus gz2. Now, though the steam going through the turbine is at a higher temperature, let us assume that the turbine is insulated, as if it is insulated, as if there is very less amount of heat transfer out of this turbine here. Now, when I say the heat transfer is zero, so please note that practically it is not zero. Practically, if actually you cannot touch to this surface, it is so hot here. But when I say heat transfer is zero, it means comparing with the other quantities, the numerical values of other quantities, I can assume that heat transfer is almost negligible, so zero. Then what about the potential energy difference? The location at the entry and the location at the exit. The location at the entry and the location at the exit. So these are the horizontal positions. The outlet is taken right here, but the location at which the steam enters and the location at which the steam exits is same. So I will cancel out the potential energy term. Now velocity. Here there is a certain pressure, temperature and enthalpy. So there is a certain velocity, no doubt there is a certain velocity, and that steam will come out. So at the exit and at the entry, at the inlet and outlet, there will be the continuity equation A1 V1. So rho AV is equal to rho AV. At the entry, the velocity would be very high, and at the exit, the velocity will be very low. But again, whatever their square, those will be much more comparable to each other. So again, I am cancelling out the velocity term. It do not mean that I am saying that velocity is zero. No, velocity will never be zero. But compared with the other quantities, this difference of kinetic energy can be neglected. So what term I finally get is H1 is equal to H2 plus W. So work of a turbine will be equal to H1 minus H2. Now this system produces work, means work goes out of the boundary of the system. Work goes out of the boundary of the system. See, through this shaft it goes out. Now we can attach any other instrument here, any other device. So this is a higher enthalpy and this is a lower enthalpy. So in the turbine we get work on the expense of enthalpy. The enthalpy reduces. The reduction in the enthalpy is equal to the work output of the turbine. Okay. So if you want to find out how much is the work of a turbine, you simply need to know only the enthalpy at the inlet, enthalpy at the outlet. Exactly same way for the nozzle. You only need to know enthalpy at the inlet and outlet. Whatever their difference, you can find out the velocity in the case of nozzle. Whatever the difference of the enthalpies, we can find out the work done for the turbine. Okay, so this is the application of first law of thermodynamics to the turbine, or energy conservation equation, or energy balance equation. So note down, this energy enthalpy is related to the substance that is transferring out of the boundary of the system, out of the boundary of the system. Now, this is the energy in transfer, this is the energy inside the mass of the substance. Oh, here there is a power failure, please wait a minute. Okay. Uh, so now pay attention to the compressor. So what basically a compressor means? So to compress will generally mean to accommodate more number of particles, more mass in a smaller and smaller volume. So the pressure increases. So what is the basic function of the compressor? Am I audible?
Yes, sir.
Okay. So what is the basic function of a compressor? Is to increase the pressure. Now to increase the pressure on its own, naturally, this process will not occur spontaneously. So for that we need to give some energy. So for this, say there is one mechanism, reciprocating mechanism, another mechanism in which on the shaft there is a certain arrangement called as blades. So the air motion happens in an axial direction, axis of the compressor, axis of the shaft. So air gets compressed. There is another mechanism. So at the entry, look at the blue colored air, and then here there is a centrifugal force. So basically the velocity increases. We are using a centrifugal force of an impeller, and that kinetic energy is then converted into pressure form of energy, and then at the red side you see the higher pressure. Another design at the inlet, look at the blue colored say air or any gas or any fluid. So that will be crushed in between the two teeth and recessed surfaces, and then because of that so-called pushing action against each other, we get or more mass of the substance gets accumulated in a smaller and smaller volume. Means the density increases, and that process is called as compression process or increase of pressure process. Again, what mechanism is actually used for the compressor? Right now in the study of thermodynamics, we will not bother about these four mechanisms here. The mechanism design will be different according to its application. But finally, If we apply the steady flow energy equation, always pay attention. There is one inlet, point 1, point 2 outlet. At the inlet, there is a temperature, pressure, specific volume, velocity, potential energy. At the exit, temperature, pressure, specific volume or density, velocity, potential energy, the corresponding elevation. So finally, what I can write down is, now this is a steady flow, so mass entering will be mass exit. So let us say mass entering is u1 plus p1 v1 plus v1 square by 2 plus gz1 plus heat transfer is equal to m2 u2 plus p2 v2 plus v2 square by 2 plus gz2 plus w. Once you write down this equation, then think about the simplification for this equation. So which energies we can say neglect, or which energies we can which are significant. So I can say that the cross section, this pipeline and this pipeline, the velocities I can neglect, so I can neglect this term. The potential energy term I can neglect it. Then what about say u1 p1 v1? Okay, so I will write down mass into h1 plus, in some cases because of the compression process we can think about the heat transfer is equal to the mass into enthalpy is mh2 plus work transfer. Again I can simplify this. If I assume that the compressor is insulated, why my assumption is correct? If I look at the energies involved here, so I can again neglect this q. So finally what I get is the mh1 is equal to mh2 plus w. Now this w is work of compression, so wc. Now for the say suppose if you are using a centrifugal pump, means this on the right hand side top side figure, centrifugal pump, I can say that the temperature are not changing, so u1 u2 are almost remaining same. So I may write down one equation like this. So m into p1 v1. Now depending upon your application, there if the velocities cannot be neglected, then write down v1 square by 2, then gz1, something like this. So here there is a underground tank, water tank. Here there is a pump, and the pump is pumping the water to a overhead tank. So the potential energy changes cannot be neglected. Is equal to, now the heat transfer is 0 is equal to, so m at the outlet the same mass will go out as that what it will come in, into p2 v2 plus if the velocity is not to be neglected, then you have to consider this, otherwise you can cancel out these velocity terms, plus gz2 plus w. Now if this is a work done of compression or pumping, means what? Somebody has to rotate this shaft, somebody has to rotate this, say, crankshaft, somebody has to rotate the driving shaft of these lobes. At the center there is a shaft here, so at the back side there is a certain mechanism, say a turbine, a electric motor, so that will be giving the energy to these turbine blades. So the work energy is, really speaking, it is minus W. Our sign convention is this way. So let it be, you can use this equation or you can use this equation. So it depends upon your application, it depends upon the situation at a particular location inside your system, which energy to be considered, which energy can be neglected. So finally, the basic form of this equation is that work of compression will be equal to final enthalpy minus initial enthalpy. So what does it mean? When we supply the energy in the form of work, where it goes in increasing the enthalpy. Now in the increasing in the enthalpy means U plus PV. So if suppose U and specific volume, internal energy and specific volume are not changing, means temperature and density is not changing, then the work will have direct effect on the pressure. So basically pressure increases when we supply work energy. Okay, so whatever the equation which right now we have written is the application of the steady flow energy equation to the compressor. In the last lecture we have completed about the application of the steady flow energy equation to a boiler. Okay, so boiler basically a heat exchanger, so heat transfer will be the enthalpy difference. The heat transfer will be enthalpy difference. Here work transfer will be the enthalpy difference. For the turbine, the work transfer will be the enthalpy difference. For the nozzle, kinetic energy change occurs because of the enthalpy difference. All of them combined together. Okay, so look at a mouse cursor. So this is a shaft, a common shaft. Onto this common shaft, at the entry, look at the shape. Okay, it is converging shape. So for a compression process, increase in the pressure process, this is a converging shape. Now there is one another mechanism which will increase the pressure, so this portion is called as compressor. Now into this compressor, after the higher pressure air, when it will come into a chamber, here we add a fuel through this fuel nozzle. So this is a combustion reaction. So we get high pressure, high temperature gases, and these gases will pass through a diverging section. This section is a diverging section. So here this is a turbine. After this diverging section, at the exit here, it can be a converging diverging section, or only a converging section, or a diverging section. Any of the combination, either this or this or this. So here it is a nozzle. Okay, so this way any engine, so right now this figure is that of a gas turbine engine. Instead of a axial compressor, if you incorporate a reciprocating compressor, you call that engine. Instead of this turbine using an axial turbine, if you make use of a reciprocating form of mechanism to transfer the motion, you call it as internal combustion engine, huh? Auto engine, diesel engine, whatever that is. So basically what changes is the actual mechanism. As far as our course is concerned, we will only look at the energies in. So what is enthalpy here? What is enthalpy here? What happens to the enthalpy? What happens to the enthalpy? What happens to the enthalpy? What happens to the enthalpy here? What happens to the enthalpy here? So that is why enthalpy is one of the very important parameter whenever we consider a flow of fluid. For every flowing fluid, you must consider the enthalpy value, as that energy is all associated or inside the substance. And all these are the mechanical devices, all these mechanisms are the means to convert the one form of energy to another form of energy. And thus we say that we have say made one in say engine. Okay, so this is another part, say a design part. Okay, so we have completed here our discussions about the steady flow energy equation, or the application of the first law of thermodynamics to the various devices. So whenever you happen to see a very large device, divide it into number of parts like this. So for each part, use the steady flow energy equation. The velocity which is going out of one stage would be the entry, will be the entry to the another. Say enthalpy of the previous stage would be the enthalpy at the inlet of the next stage. Say any of the pressure at the back stage will be the pressure at the forefront stage. So all these property values, say temperature, internal energy, pressure, specific volume, velocity, position, work transfer is to be calculated across the engine, heat transfer to be calculated across that particular section. So combining these parameters, apply them at the inlet outlet. Once inlet Once outlet is another's inlet, its outlet is another's inlet. So the parameters here, say P1, this is the location 2, say this is the location 3. So T3, U3, P3, V3, velocity 3, Z3. Now whatever has happened here are the heat transfers, work transfers. So they will combine together, they will, whatever the energy is there, that will dance in between these forms of energies. Might be work will get transferred to the pressure, or to the temperature, or to the both, means enthalpy. If the fluid is compressible, its density would change depending upon the shape. Look at his, this is a reducing cross section, so this entire shape will act like a nozzle, so velocity would change. The potential energy, most of the cases we can neglect it, because our engines will be, say, the horizontal, even if it is a vertical, or even if there is a difference according to your application, you can consider those parameters. Okay, so likewise, this is a fourth stage. This is the fourth cross-sectional location. This is fifth. This is sixth. So once you start from one parameter value set of values, you can solve all these equations, and then you are able to know what exactly, how exactly the energies are transferred within themselves, where we add energy, so through the chemical reaction at the combustion of the fuel and air, oxygen, and hence we can find out, we can know that how the energies play. We can quantify the energies, and once you quantify the energies, this energy quantity will tell you how much force will be generated. This force